All right, just like previously, what I think I'm going to do is blather a little bit about this topic of this current lab, and that's going to be about magnetism and Faraday's law of induction. Okay, so first of all, we're all familiar with magnetic force. It's kind of creepy and weird because it's, again, an unseen force, much like electrostatics. So let's just note then that it's also unique like electrostatics because it can be both attractive or repulsive. Now, this is in contrast to something like gravity. Gravity is only attractive, that's it. And all masses pull on each other with a gravitational force. The gravitational constant is a tiny, tiny number. So the masses involved in gravitational force have to be huge in order for it to have any noticeable effect. But for electricity or magnetism, the force, the constant that pervades the universe for electrostatic or even magnetic force is quite large. For an instance, for electrostatics, it's about 20 powers of 10 bigger in magnitude. So it's a 20 power of 10 stronger force than gravity. So what that means is you only need tiny amounts of charge for the force to become noticeable. And the same thing is true in magnetism, not to the exact same extent. Magnetism isn't quite as powerful as electrostatics, but there is attractive and repulsive force in magnetostatics, just like there is in electrostatics. Now, interestingly, gravity, as I said, only works one way, and in that sense, you don't need flavors of magnetism, meaning you don't need to indicate which way the action will occur. We use plus and minus with charge, and you can think of it really as like a positive or negative direction on the number scale that the force ultimately is acting on when you're being either pulled or pushed by electrostatics. In magnets, due to the connection with navigation on the Earth, we call the flavors of magnetism north and south. So a north magnetic pole points towards the north pole of the Earth. So the north pole pulls up towards the north pole of the Earth, which is located in the Arctic, and the south magnetic pole will move a compass needle to the south down towards the so-called bottom of the Earth, which would be Antarctica. We're all familiar with permanent magnets. They usually come in bar or horseshoe shapes. These are chunks of metal which can exert magnetic force. And first of all, an interesting point about a so-called bar magnet is that they all have both a north and south pole built into them, all the way down to the nanoscopic level. So we would term these devices magnetic dipoles. And as a matter of fact, you cannot isolate a so-called magnetic monopole. You can't isolate a north and a south. If you take any bar magnet and cut it in half, you will generate two new dipoles, each having a north and a south. So as we've said, magnetism exhibits the property, just like electrostatics, of being either attractive or repulsive, as opposed to gravity, which is only attractive. So what we note is that just like in electrostatics, like repels like, so positive charges push each other away from one another, negative charges push each other away from one another. Here in the realm of magnets, north poles will exert a force of repulsion upon each other. South poles will exert a force of repulsion upon one another. This is an artifact of Newton's third law. Newton's third law says for every action, there is equal an opposite reaction. So if the bar magnet on the left is being pushed to the left by the repulsion of another, the bar magnet on the right is being pushed equally, meaning the magnitude of magnetic force that it feels is equal, but the direction, as Newton's third law describes, is opposite. So the magnet on the right is pushed to the right, while the magnet on the left is pushed to the left when you put the same poles in proximity to one another. Now, if you put opposite poles in proximity, put a north to a south or a south to a north, then they exhibit attractive force, and the forces pull inward towards one another. And again, artifact of Newton's third law, the magnet on the left will pull the magnet on the right just as hard as the magnet on the right pulls the magnet on the left. Now again, this is interesting that even if the magnet on the left is stronger than the magnet on the right, maybe it has twice as much magnetic strength as the magnet on the right, that doesn't matter. The attractive force that the left magnet exerts on the right magnet is equal to the attractive force that the right magnet exerts on the left magnet. Same thing is true with charge. Same thing like that is true with gravity. Okay, but again, that's not only are the magnitudes equal, but their directions are opposite. Notice the force vectors of attraction are pointing inward towards one another in opposite directions when you put opposite poles near one another. That's my phone ringing, but I'm not even going to stop it. Even more important than in the electric field case, we often discuss the behavior of magnetic phenomena with magnetic fields. And so fields themselves are just bizarre things to begin with. Fields create action at a distance, meaning you don't literally have to contact an object to exert force. So if you or I want to exert force, or a car or a steam shovel wants to exert force, literally you, me, the steam shovel, or the car must touch the object that it's exerting force on. Fields like gravity, electrostatics, or magnetics do not have to touch the object, but the force just emanates through space. Very interesting, very bizarre. Okay, so we're going to have to be able to represent a magnetic field much like we represented a gravitational field. This is going to be very important when we talk about induction. Now, one thing I mentioned here is that the magnetic field, just like electric fields and gravitational fields, are conservative. That means they store energy. You can deposit energy into the field, and then you can recoup that energy later. It can be converted between potential and kinetic forms, just like you can do in lifting a rock up on a ledge and then pushing it off the ledge and changing it to kinetic. You can move a charge around in a magnetic field and have force applied to it to accelerate that charge. So let's look then at how we will describe a magnetic field. As we show in this cartoon, we will have some fictitious magnetic field lines. They are typically represented by the capital letter B, and the magnetic field lines, and notice I have a little vector hat on the B indicating it's a vector field. It has magnitude and direction. So what we do by convention is that we claim magnetic field lines emanate outward from a north pole. Magnetic field lines emanate inward towards a south pole. Now, magnetic field strength in its so-called SI derived unit is a Newton divided by an amp divided by a meter, which in its base units is kilogram amp per second squared. Now, that turns out to be a very powerful magnetic field, usually too powerful for which we will typically describe things. So other magnetic field units such as Gauss are going to be used, which are fractions of Tesla. But Tesla is the one we are supposed to use when we describe the magnitude. Now the direction again is going to be a choice. So in other words, if you have another North Pole, fictitious North Pole, in the proximity of a North Pole, it will be repelled. That's why the field lines are moving away from north. If you have a fictitious North Pole and bring it towards a real South Pole, it'll be pulled towards it. So the field lines emanate inward towards a South Pole. There's another important difference with the magnetic phenomena than the electrostatic, and that is because since all magnets are dipoles, meaning all magnets contain both north and south, you're going to have some field lines that are ultimately going to be drawn, pushing out of and drawing back into any magnetic material. If to contrast that, if you have you can have a positive point charge which only has electrostatic lines coming outward from it. You can have a negative point charge which only has electric field lines going inward towards it. Here I'm showing first a single bar magnet in the top left, and you'll see that the field lines emanate outward from the north, and if there was no South Pole, they would just go, and it was a point, they would look much like a positive electrostatic point charge. They just radially emanate outward, but because the South Pole is on the other end, the field lines bend around and return towards the South Pole. Now notice in the middle top picture, I put opposite poles of magnets near each other. You get an intensification of the field lines between the North and South Pole. Now, one thing you should note is that the density of the lines, the spacing of the lines says something about the field strength. The closer the lines are together, the stronger the field is. So because of that fact, in the top middle picture, we have an intense north to south straight magnetic field line going from the north to the South Pole, a fairly high intensity, and then outward from that we have emanating field lines of decreasing strength the further you get away. Now if you put two like poles next to each other like we did in the top right, you will see that these are two south poles pointing towards each other. The bottom left picture is the top right is two north poles pointing towards each other. The bottom left is two south poles pointing towards each other. They make similar field lines, except for the fact that the South Pole field lines emanate inward. The North Pole field lines radiate outward. You see the void space in between them where the net magnetic field due to both is going to cancel. There'll be a zero magnetic field there in the center between them. What a horseshoe magnet ends up being is a bent over bar magnet, putting the north and south poles in proximity to one another and intensifying the field strength between the close poles in proximity, so that you see when I draw the field lines looking like for that north-south horseshoe magnet. With regard to the Earth's magnetic field, first of all, maybe we should mention what generates the Earth's magnetic field. We haven't even really mentioned what generates the magnetic phenomenon at all. The magnetic phenomenon is generated by charge and motion. So if you move positive charges or you move negative charges, you are generating magnets. Actually, what you're doing is you're actually making the individual poles. A north magnetic pole or a south magnetic pole can be generated by moving a positive or a negative charge. And then how a permanent magnet works, or how the Earth works as a magnet, is that anytime charge is in motion, you create magnets. Well, the center of the Earth is molten ionized iron, very hot, very liquid, very mobile because it has currents flowing around of this charged species in the center of the Earth. This liquefied, crazy hot iron ions moving around and around in currents emanate with this charge in motion a magnetic field. This magnetic field emanates from the Earth in the way you see here, with the South Pole moving out of the top of the Earth and the North Pole moving out of the bottom of the magnetic field of the Earth. This is in order for the north magnetic needle of the compass to be attracted. If the north needle of the magnet is attracted, it is pulled toward a south pole. So the interesting point would be that the north pole of the Earth is actually a south magnetic pole. The south pole of the Earth is actually a north magnetic pole. That's kind of weird. I guess that confuses Santa Claus for that reason. Interestingly, also, the magnetic poles of the Earth have shifted dramatically over the eons of time that the Earth has been around. The currents of molten charged iron in the center eddy and flow in different directions over the epochs of time. So the magnetic field of the Earth has varied over time depending on how that charge is flowing, how the direction of that charge flowing changes. So there's been many noted geologic periods where there's been very low magnetic field on the Earth, very intense magnetic field, and very different orientations of the magnetic poles on the field of Earth. So this idea of charge in motion creating magnetic field is going to be very important when we talk about Faraday's law of induction a little bit later. So far we've mentioned that charge in motion creates a magnetic field. Well, current carrying wires are charge in motion. So current carrying wires generate a magnetic field. So how do you recognize the direction of a magnetic field due to a current carrying wire? What we use is the magnetic field right-hand rule, which says to find the direction of the magnetic field due to a current carrying wire, point the thumb of your right hand in the direction of the current. So this is why you use the right hand, because that's for the positive direction of flow of charge. Remember, I is the direction that positive charge would move in a circuit. So your thumb of your right hand points in the direction of the current, and then your fingers wrap around the wire in the direction of the magnetic field. It's going to take 3 dimensions of space to represent the direction of flow of movement of charge and the magnetic field that that motion generates. So when we're using PowerPoint slides or the chalkboard or whatever, which is a 2-dimensional surface, we need to somehow be able to place the 3rd dimension into these pictures so that we can understand and interpret what's going on. So I'm going to use a notation that I'm showing on this slide. I'm not sure if this is exactly what you're doing in lecture or not, but this is how I have always done it, and this is how I'm going to do it. When I have a vector pointing out of the page, I draw a circle with a dot in the middle of the circle. This can be for a field line or a direction of movement or whatever I want, but if it's moving to the left or the right, I just draw the arrow on the page left or right. If it's moving up and down on the page, I draw an arrow up or down. But if it's coming out of the page, popping right into your face, I'm going to draw a circle with a dot in the middle. What you should think of that is as like the tip of an arrow. Now, if I want to show motion or indicate motion going into the page, so it'd be hitting the page then going behind it, I'm going to draw a circle with an X. What I want you to think of that as meaning is the tail of an arrow. So if the arrow is flying through the page, you would see its tail. If the arrow is flying at you out of the page, you would see its tip. So the circle with the dot is the tip of the arrow, it's coming out at you. The circle with the X is the tail of the arrow, it's going into the page. That's how I'm going to represent the third dimension of space. Now again, on the page, I can show X as being left or right and Y as being up or down. So these two new things are going to represent Z, coming out of or into the page. So if I have a current carrying wire, as you see on the bottom left, with I indicated going from left to right, now I'm going to use the right hand rule. I'm going to place my thumb in the direction of that I arrow. Notice then my fingers would naturally curl above that line so that I see you circle with dot, meaning the magnetic field generated by charge flowing in the direction from left to right is such that the magnetic field B would be coming out of the page above the line. Now notice my fingers wrap around the wire, and by the time I got to the bottom of the wire, my fingers would be pointing into the page. So I will put circles with X's below the I flow direction, indicating that at those points, the magnetic field generated by the charge in motion is going into the page. So the charge is going from left to right. The magnetic field generated by that charge in motion is coming out of the page above the wire, circling downward above the wire, and then heading into the page going below the wire. Now on the right, I'm indicating what would happen if the current is coming right at you. So in the third dimension of space, if you like, the Z direction, I'm putting the current as flowing as the tip of an arrow, or the current is flowing right at my face. Now I point my thumb in the direction of the flow of charge, which is coming out of the page. Then my fingers are naturally curling, so they are moving counterclockwise around the wire. Notice the direction of arrow movement around that eye coming towards you is counterclockwise. If the current were going into the page, I would point my thumb towards the page, and my fingers would naturally be curling in a clockwise fashion around the wire. Let's use these ideas to discuss the behavior of a so-called solenoid. A solenoid goes by other names in electromagnetic theory. It goes by the name of a coil, because it's a loop or coil of conductor. And it also goes by the name inductor. And that talks in terms of Faraday's law of induction. So a solenoid can often be replaced by the name coil, can often be replaced by the name inductor. So again, a solenoid is a continuous loop of conducting material. And this conducting material can support the flow of charge in it. So let's suppose I have, as I show on the top right, a coil of wire, which should really be three-dimensional. Let's assume it's coming out of the page. The coil is not flat on the page. The coil is sticking up out of the page and going back behind the page. But I'm just looking at it in this two-dimensional representation. So it is what it is. And let's suppose this conducting loop, this coil, has a current flowing in it. And at the top of the loop, I have drawn a circle with a dot, which means the current is coming out of the top of the page. And at the bottom of the loop, I'm drawing a circle with an X. That means at the bottom of the page, the current flowing through this conducting loop is going into the page. So again, it's a three-dimensional picture I'm trying to represent. Current coming out at the top, flowing above the page between the top and bottom of the loop, then heading into the page at the bottom, then would be flowing upward behind the page until it got back to the top of the loop. So this is a continuous loop where charge is flowing through it. I can use my right-hand rule to say which way the magnetic field will be generated by this loop. So coming out at the top, I put my thumb pointing outward, my fingers curl around. Inside the loop, the B field is pointing to the left. You should verify that with your own right hand. Thumb placed coming out of the top of the loop, fingers curling around the loop. Now I'm not talking about outside the loop, I'm talking about inside the loop. The B field points to the right. Now as I come down the loop towards the bottom of it, my fingers are still pointing inside the loop to the right, so the B field is still in the loop as I come down towards the bottom. When I get to the bottom, the current flows into the page. Point your thumb in the direction of current flow. Inside the loop, your fingers are curling to the right. So as this charge moves around the loop, around this particular coil, it will constantly be generating a B field which has vector direction pointing to the right. Now, if I have, in fact, a solenoid is many, many, many loops of continuously connected conductor. These are turns of the coil, as it is known. Each loop represents its own, will generate its own magnetic field. These magnetic fields, since the current is flowing through each loop in the same fashion, out at the top, in at the bottom, each loop will generate its own B field pointing to the right. These vectors will be constructively working together and add together. So inside the inductor, inside the solenoid, inside the coils, you will get an intense magnetic field. So B of the solenoid will be the sum of the B of each of the field. Each individual coil can be found from calculus to generate a magnetic field of mu I over 2R for each loop, where mu is the permeability of free space. This is how a magnetic field operates in a vacuum. Air is close enough to a vacuum. We can use that value for the behavior of the field. Now when I have this coil, which is a connected series of loops, for each coil I will generate that same magnetic field within the loop of value mu I over 2R. And now I'll just multiply that by n for the number of turns in the solenoid, and the total magnetic field is given by that expression you see at the bottom right. Now, we're not really going to play much with that expression today, but you probably played with it in lecture instead of here in lab. Before we can talk about Faraday's law of induction, I have to mention the concept of magnetic flux. I'm sure you've talked about it in lecture. It's a little bit of a weird abstract concept. Essentially what magnetic flux means is how many magnetic field lines, or the density of magnetic field strength, that can be enclosed by a particular surface. Now the surface you choose to enclose the magnetic field strength is completely arbitrary. It can be a little tiny area through which the magnetic field lines are passing. It could be a huge, huge section of space, any geometric shape you want, and we allow it to have an electric field flowing through that area. Now the formula for this magnetic flux, it's given symbol capital Phi. It is equal to B, the magnetic field magnitude, times A, the area of the shape that is encapsulating the lines, times the angle that the two B and A's make relative to each other for the normal of the area's surface, times the magnetic field strength, magnitude if you like. Take the cosine of that angle between the two. I will capture more and more field lines as theta goes to 0, I will capture less and less field lines as theta goes to 90, so that the cosine of theta goes from 1 when the angle is 0 to 90 at 90 degrees cosine theta of 0. So you're capturing no flux if the surface is perpendicular to the field. Scratch that. You're capturing no flux if the surface is parallel to the field. You're capturing the entirety of the flux if the surface is perpendicular to the field based on that behavior of the angle. Now look, we're not going to do calculations involving the magnitude of flux here. We're just going to use the concept of flux to help us understand Faraday's law of induction. So again, I'm sure you spent a lot more time talking about this in lecture. Flux is some sort of a fictitious quantity, if you like. You pick an arbitrary surface, you let magnetic field pass through this surface, and the amount of magnetic field being captured by this arbitrary surface is the flux passing through that surface. That's really all we need to know about it. Again, you can tune into lecture if you want to learn a little bit more about calculations involving flux magnitude. Okay, now what we're going to do then is talk a little bit about Faraday's law of induction. And the idea behind it began when Hans Christian Ørsted, a Danish physicist, noted that when he had a current-carrying wire, it could make a magnetic field. And he actually discovered this when he was given a public demonstration and had some compasses laying on a table. And when he hooked a battery up to a circuit, he noticed all the magnets jump, or the compasses jumping. And that told him that something weird was going on. He was generating a magnetic field when he was altering the current flowing through the conductor. So the conclusion was that charge in motion could generate a magnetic field. Well, what Michael Faraday, a great English scientist of the mid-1800s, what he tried to find out was the reverse true? Meaning, could moving a magnetic field or a magnetic field changing, could that generate a current? So again, Ørsted noted that a changing current in a wire made a magnet, and Faraday wanted to see if moving or changing a magnet could produce a current. Essentially, we can describe Faraday's induction in the following fashion. I will design two separate circuits, and they are known as the primary circuit and the so-called secondary circuit. In the primary circuit, I will make it a DC circuit where I have direct current flowing when I close the switch through the power supply, through the resistor, and then in a continuous loop back to the power supply. Then I'm going to wrap part of this conductor around a ferromagnetic material, something that can support magnetism within it. Now, I'm not going to flow current directly through this conducting magnetic, or this connecting magnetic bar, but I am going to wrap the current around the bar, both conducting wires from the primary circuit and conducting wires from the secondary circuit. Now, in the secondary circuit, there is no power supply, and there's no way for the current to flow through the ferromagnetic material connecting the two so that current is hopping over to the second circuit. But what is possible is that the coils from the primary around the conducting ferromagnetic, the magnetic material, can, as the charge flows over this, these are inside the loops of a solenoid, if you like, and inside those loops, I will be generating a magnetic field. So there will be a magnetic field that is transferred from the primary into the coils of the solenoid of the secondary. Now, it turns out, as long as the current is constant, as it should be in a direct current circuit, then there's really nothing of interest in the secondary circuit. Constant current in the primary circuit generates a constant magnetic field in the secondary circuit, and that has no influence on a current in the secondary circuit. But when there is a changing magnetic field in the core material, we call that the core around which the coils are wrapped. If the core experiences a changing magnetic field, when would that occur? If the DC current is suddenly reversed, if the DC current is suddenly raised, if the DC current is suddenly lowered. For the instant that the current is reversed, raised, or lowered, there's a changing magnetic field in the core. And anytime there is a changing magnetic field, there will be an induced current in the secondary circuit, even though it does not itself contain a power supply. So in the Faraday experiment, we see that a change in current in the primary, which is connected to the secondary by a core of ferromagnetic material, which can have a magnetic field associated with it. Then when you change the current in the primary, you induce a current in the secondary. That's known as Faraday's law of induction. And in lecture, you probably spent a little more time on this. What we note is that the electromotive force, or EMF, which is generated by the mechanical change of the current in the primary and what is induced in the secondary, will be equal to the formula minus N times delta phi delta T. And let's say a little bit about what those quantities mean. Delta phi is the change in flux through the coils. This is where and why we had to talk a little bit about flux. When we have a changing flux, we can induce current into the coil. Notice, the quicker the flux changes, the more EMF that is induced in the secondary. Because if delta T gets smaller, delta E gets bigger, or E gets bigger. The magnitude of the change of flux makes E get bigger. And also notice that there's an N factor. And N is the number of turns in the solenoid. Remember, the core is wrapped by the conductor. The wrapping around the core generates a so-called solenoid, and you can count how many times you wrap around this solenoid to give you the number of turns in the solenoid. That would be that would be N times delta phi delta T. Now, what is the minus sign all about? Well, what we're going to notice is that it's going to be a fact that we can have a flow of voltage in one direction, or we can have a change in electric potential or change in voltage in one direction or another. And essentially what the minus sign is saying is that the induced EMF is in opposition to the change in flux. That's maybe what you should think of this minus sign implying. The change in direction will induce the opposite effect from the primary to the secondary, and that's probably what we should think that this sign is implying. Now again, in this particular instance, we're not going to do much with this formula. You probably did more with it in lecture. Faraday's law of induction is a demonstration of what is known as Lenz's law, which is a little more general idea here. The minus sign in Faraday's law is one of the consequences of so-called Lenz's law, which says that a conductor which experiences a change of magnetic flux, that's the delta phi delta t, generates a current that creates a magnetic field to oppose the change of flux that it experiences. So here's essentially what Lenz's law is saying. When you attempt to change flux, a conductor doesn't like change in flux. A conductor likes steady flux. So when you make a move to change the flux, the conductor makes a move to do the opposite. So if you attempt to lower the flux flowing through a conductor, the conductor magically moves charge to build back up the loss of flux that it experienced. Or if you have a constant flux through a conducting surface, now you increase the flux through that conducting surface suddenly. The conductor doesn't like that. It moves charge in a direction to fight against the increase that you're imposing on it. It moves charge in a direction to create an opposing or negative sign, opposite flowing flux of its own, to combat what change in flux you have given it. Let's look at applications of Lenz's law to the coil of a solenoid. Okay, so I have a conducting loop, which it looks like it's flat on the page, but it's coming out of the page and going behind the page, let's assume. And it's doing so that I can slide a bar magnet inside and out of the loop. Let's start with the upper left-hand picture. I have the north pole of the magnet facing the loop, and the arrow indicates I'm pushing the bar magnet's north pole into the loop. That is going to induce a changing flux inside the loop. Of course, as the coil, the bar gets closer to the coil, magnetic field strength grows in the coil, so the flux is increasing in the coil as I push the bar magnet's north pole towards the coil. The coil says, I don't like that. I want to stop that from happening. I'm going to induce my own magnetic field in opposition to the field lines of the bar magnet increasing my flux. So the induced magnetic field, which is indicated by the thicker arrow, is to the left as there's an increase of flux due to the bar magnet moving to the right, and the outward pointing field lines coming in to increase the flux. How then can the conductor make an opposing B induced to the permanent increasing B of the bar? Well, what it does, as you can see, is induces a current to flow in the conductor. If I take my fingers of my right hand inside the loop and note the direction that my thumb must be for my fingers to point to the left inside the loop, at the bottom of the loop, my thumb is pointing towards me. I would draw a circle with a dot indicating the current induced in the loop by this change in magnetic flux in the loop will be coming out of the bottom of the loop. Now my fingers stay pointing to the right as I slide up that loop outside of the page. When I get to the top of the page, the top of where the coil is going in, now my thumb is pointing into the page to keep my fingers pointing to the right, which is the way I want the coil to induce a magnetic field to oppose the change in flux. That means the current is heading into the loop at the top of the circle. Now let's move to the top right picture, where I again have a north magnetic pole facing the loop, but now the arrow is indicating I'm pulling the north magnetic pole away from the loop. If the loop, again, if the magnetic magnetic bar is stationary, then there's no change in flux. As soon as I begin to pull the bar away, I'm going to be decreasing flux in the loop. Now, the field lines emanating from the pole of the magnet in the loop are pointing to the right. As I pull the bar to the left, I'm decreasing those right-pointing magnetic field lines in the loop. The loop says I don't like that. I need more right-pointing B field lines in me. So I will induce a current in me to make a B induced pointing to the right. To do so, I will curl my fingers so that my fingers are pointing to the right. This gets a little bit tricky to do because my fingers want to act weird, but inside the loop, my thumb is coming out at the top. So I'll have a circle with a dot at the top, and keeping my fingers sliding down to the bottom, I have my thumb pointing into the page to induce my, inside the loop, my induced field to be generated to the right inside the loop. I have current coming out. The same thing can now be done with the south pole. The bottom two pictures show moving the south pole either away or the south pole towards the conducting loop. When I move the south pole away, remember field lines are going towards the south pole. So as I move the south pole away, I'm decreasing field lines pointing to the left. The loop will try to make more field lines pointing to the left to get my fingers to curl to the left in the loop. The current must come out at the bottom and in at the top. And then on the right bottom corner picture, I'm again going to just move the south pole, but this time towards the conducting loop. The field lines that I'm generating are such that they're heading on the bar magnet towards the south pole. And since I'm pushing toward lines to the loop, it works against that. Lenz's law says do the opposite. So the opposite would be to induce a field of north pointing lines in the direction that you see to oppose the increase of south pointing lines as the bar magnet slides inward. To make that north pole pointing to the right induced field, I curl my fingers around inside the loop. My thumb would be pointing out at the top and coming in at the bottom. Now notice if I just take one of these bar magnets and move it in and out, in and out, in and out constantly, what I would see is a time frequency spaced change of the current flowing from the top to the bottom, bottom to the top, top to the bottom, bottom to the top. As I move the coil, let's say I move the north pole in, the current will be such that it's coming out at the top. When I'm pulling the north pole out, say that again. When I move the north pole in, the current will be moving in at the top of the loops. When I pull the north pole out of the solenoid, the current will be flowing out at the top of the loop. And as I continue to do this, I would generate a so-called electromotive force of pushing this, mechanically moving the magnet in and out. I can generate a steady alternating current in the loop, and it turns out that's what the power company does for us. Let's look at some examples of how we can use Lenz's law to predict the direction of a current flow. You might see something like this on some quiz questions. Suppose I have a ring at the top left corner of this slide that is falling outside of a B field. Well, if it's outside the B field, it has no flux in it. If it had no flux in it as it's falling, it doesn't have any change in flux. So there will be no current induced in a ring because it has no changing flux. Now, let's look as the ring continues to fall, and now it begins to enter a B field. The B field is indicated by the black circles with crosses on them. That means the B field is going into the page. So the B field is falling into a B field going into the page. That means it's as it falls into the field, not as it's outside of it, but as it enters this field. It's got a changing flux. And as it gets deeper and deeper until it's immersed in the field, it will continue to have a changing flux. While it has that changing flux, it says, no, 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 I don't want a changing flux. I must do something to oppose the flux change. Since the changing flux is heading into the page, it generates its own magnetic field coming out of the page, indicated by the red circle and dot inside the sphere as it falls into the field. So I need a magnetic field coming out of the ring as it falls into the field. Point my fingers, in the direction of that dot, circle dot, coming out at me. My thumb points in a counterclockwise direction. So as I have changing flux, as the conducting ring falls into the field, I will induce a current in the ring that heads counterclockwise around the ring. Now, let's look at the center one. As the ring is in the field and it is falling, the spacing of the magnetic field dots is indicating there's a constant magnetic field as it falls in that field. That constant magnetic field is putting the same flux through it at all points as it falls in that field. So as it is in the constant magnetic field, it experiences no change in flux, and so there will be no induced current in the ring. Now I will point out to you, as the ring exits the field, it will be experiencing a decrease of flux going into the page. It will work to oppose that. It will generate its own flux coming out of the page, since it's losing flux going into the page, it'll generate flux going into the page. You could think about which way the current will be developed for that in case you get asked that later. Now again, once it's falling outside the page, or outside the field, there's no flux in it, so there's no need to generate a current because there's no changing flux that it's experiencing.